Well, I've been promising for a while now that we're going to learn about the cool stuff here, at least as it applies to engineering and physics, that type of stuff, math, more math, that we're going to start to work with vectors a little bit. We've learned the basic of what a vector is and how big it is and which way it points, but now we're going to actually do some work with it. And the first topic we're going to cover is called the dot product. So without further ado, let us begin. But let us begin in full screen. There we are. And we'll begin in black. Vector dot product. Now this is when it starts to get really good. The dot product is also sometimes called the scalar product, and you'll see why in a sec. The scalar product, you might guess that the dot product generates a scalar quantity. Let's say we have two vectors, u, we're going to define as these three scalar components, u1, comma, u2, comma, u3, u2, Bono. And then the vector v, I'm going to indicate that this is a vector here. Here's where it starts to get important. I'm going to write as v1, comma, v2, comma, v3. Now it's important to note that these u's here, since they don't have a line over them, or an arrow, or a hat, or anything, or an underline, anything indicating they're a vector, these u's are scalars. This u is a vector. We define the dot product as u dot v, and that equals, are you ready? We just multiply the two x components, u1, v1, and then we say plus, whoop, that's actually not, I goofed that up. It's not a vector, it's a scalar product, right? u1, v1, plus u2, v2, plus, you guessed it, u3, v3. U, vector u, dotted with vector v gives us this sum of three scalars, u1, v1, plus u2, v2, plus u3, v3. That's it. That's the dot product. Okay, well, it was nice to work with you guys here, and we'll see you in class tomorrow. Ooh. Nope, hold on. There's a couple more things. I promised one particular student, sorry about this, so I think many of you in the fall of 2013 know what student this is, and student, you know who you are. I promised there's some relation to trig. In fact, I even made such a bold promise that vectors will help us not use trig as much anymore. So, let's quickly review, well, actually, sidebar. First, this lecture is just not going well. First we stopped it early, and then we went back, and now we're doing a sidebar already. What would happen if we dot a vector with itself? What if we did u dotted with itself? What happens there? Right, it becomes u1, or u1 squared plus u2 squared, right? u2 times u2 plus u2 squared. That would be a good band. u3 squared. Well, wait a minute. The x component squared plus the y component squared plus the z component squared. Well, that looks a lot like just the magnitude of that vector squared. So if we dot a vector with itself, we get its magnitude squared. Wow, that seems like we're going backwards fast. Well, let's take another review here. So we're still not making any progress. We're just working our way backwards. Let's review vector subtraction. And I'm going to draw two vectors here. And for lack of originality, I will call them, oh, I don't know, how about u? This is the vector u. And this is the vector v over here. Now, what would this vector be here if I did that? Remember, that's kind of the counterintuitive approach to vector subtraction. So that would be the vector. Let's see, it's if I did v, what would I have to get up to u? So that would be u minus v, that vector there. Now, if these are all in one plane and there's 3 points here, right? 3 lines, 3 points, they certainly could make a plane. And I said that there is an angle between u and v like that, theta. All right. Well, then this becomes a triangle. Now, my college math students can apply this handy little deal called the law of cosines, right? But they don't know about vectors, so we'll just do this in terms of magnitudes. We can say that the magnitude of u minus v equals, or that this thing squared, u minus c squared minus equals, let's say it's the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle between them. So the cosine of that theta thing there. All right, so that's what the law of cosines says. So that's what we learned either in your geometry class, your trig class, your pre-calc class about the law of cosines. All right, well, I could also, let's even say in a different color, in blue. I know that u minus v magnitude squared. Ooh, u minus v magnitude squared. Where have I seen a magnitude squared before? Oh, back here. Here's a magnitude squared. Why did that come from? Just dotting the vector with itself. Okay, so u minus v magnitude squared must also come from u minus v dotted with, oh, I better make room for my dot there. I'm going to be doing dot products, so I got to have room for my dots. U minus v dotted with u minus v. Those are both vectors. Now, the cool thing about the dot product, since it's really just scalars, all the same rules apply. You know, distribution, factoring, you know, subtraction, parentheses, all that kind of stuff. So I'm going to write this as u minus v dotted with u minus v. I can write this as the u dot u, vector u dotted with, that's a terrible vector sign. Let's redo that one. Vector u dotted with vector u. And then I'm going to, uv, there's 2 of those, so it's minus 2 times u times v. And then that's going to be plus, let's see, oh, down here, plus v squared, or v dot v. V dot v. All right, well, that's easy enough. But I know that u dot u and v dot v, that's just the magnitude squared. So this becomes the magnitude of u squared minus 2 times the magnitude of, oh, get rid of that. That's not a magnitude. I'm looking at my, I'm looking right above where I'm writing. 2 times u dot v, and then plus v dot v is the magnitude of v squared. So there's 2 different ways I can do this. I can say that u minus v magnitude squared, I can do this law of cosines stuff here. Or I can say u minus v magnitude squared, and I can just do it kind of like with FOIL there. So I know that u minus v magnitude squared has got to be the same as u minus v magnitude squared. So if I set those two equal to each other, what can I do? That'll have to happen on the next page. I have the magnitude of u squared. And this is a long one, so it takes me, I got to be very careful about using up my space. The magnitude of v squared minus 2 times u dot v. Right, where did that come from? That came from the FOIL version of u minus v dot u minus v. I get this thing, so I just shuffled around the order a little bit. But that equals, and this is where it gets cool, the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle between them. Did I do that right? Let's check. Sure. U minus v squared, doing the law of cosines technique, u squared, v squared, mag u squared, mag v squared, minus 2 mag u, mag v cosine of theta, versus the FOIL technique. All right, so my algebra I think is legit. So I can go back here. Let's clean house a little bit. All-powerful red pen of cancellation. We have a magnitude of u squared on both sides. That goes away. We have a magnitude of v squared on both sides. That goes away. We have a minus 2 on both sides. That goes away. And now we're left with something pretty slick. We simply have u dot v, right, which is a very easy operation to do arithmetically, equals the magnitude of u times the magnitude of v times the cosine of the angle between them. And we can shuffle this around into a slightly more useful way. I can write that the cosine of the angle between two vectors equals the dot product of those two vectors divided by the product of their magnitudes, u, v. So that is one of the rare results that I believe warrants a red box. That's huge. All right, so that's the biggest thing that we're going to take away from this dot product, is that it's related to, very much related to, the cosine of the angle between the two vectors. Okay, now, I don't know how many of you have this cable television, right? You've heard of cable television. One of the stations on the cable television is ESPN, right? I think it's exclusively sports programming network, something like that. And oftentimes on late at night, I mean, now there's like ESPN 1, 2, 3, 4, 5, 8. But on all of the ESPN channels, late night, they have this World's Strongest Man contest. And part of what they do in the World's Strongest Man contest is they have these men, and they have a rail car, and it's on rails, and then they tie a chain to it, and then they pull it with their teeth or something like that to prove that they're in fact the world's strongest. And there's always a guy, Jürgen, Sven, a German guy named like Horst or something like that. And there's always the token American guy, Bill. And the token American guy never wins. Part of the reason the token American guy, Bill, never wins is that, you know, we know the railroad tracks, although there are some bad tracks, but if the tracks go in this direction, Bill, you know, the American guy, you know, he might be a pretty strong fellow, but he pulls off, I mean, he puts the chain in his mouth and then pulls on it, but not parallel to the tracks. So we've got a problem. Bill, representing the United States on late night ESPN, trying to prove he's the world's strongest man, but he's not pulling parallel to the tracks. So we need to figure out how much of Bill's effort, so I better label this, otherwise you're going to look at the notes and wonder what's going on. So this is Bill, we'll do that in red. This is Bill. And these are the tracks. And this is the train car here. The question at hand, or at least the question I'm sure you're asking yourself, is how much of Bill's effort is aligned with the tracks. All right, that's what you've got to be asking yourself right now. For those of you who have taken a physics class, we can do a little vector decomposition here. And how does that work? We'll do that in blue. Actually, we'll do it in, I'll reproduce Bill and the tracks over here. So here's Bill, vector, here's the track, vector. And we can do this little trick, the geometric approach, where we drop this little kind of dotted line perpendicular to this. And then the component of Bill, so that's the component of Bill in the direction of the tracks. Right? So that's what we're after. Now, those of you who have taken physics and geometry, we know that what this amounts to, the amount of effort of Bill in the direction of the tracks, equals, so the scalar amount, Bill, along the tracks, equals Bill's magnitude times the cosine of theta. Where is theta, you ask? Well, theta remains the angle between those two, right? So it's the magnitude of Bill times the cosine of the angle between them. But we've got something pretty handy here. We know what the cosine is. So we can say that this thing equals the magnitude of Bill times the cosine of the angle between them. So it's Bill dot track divided by the magnitudes of Bill and the magnitude of track. Right? So this is Bill, and then this is the angle between them. Well, we get out the all-powerful red pen of cancellation again, and we can cancel out these two guys here, and so we're just left with the projection. We'll call this a projection. Projection of B onto T, and the way we write that is projection. We're trying to project onto T, so that gets a little subscript there, kind of like the base of a logarithm, of B equals, well, those two cancel out, so it's B dot T divided by the magnitude of T. Right? The reason why we divide by the magnitude of T is because we don't care, how long the tracks are. We got to, when we do B dot T, that's going to give us some big, huge number, right? If the tracks are really long, but we don't care about how long the tracks are. We just care about Bill, so we got to normalize this by the magnitude of the track vector. But we have a small problem here. This is good, so let's give this this maybe warrants a dotted red box, because it's pretty cool, but not as cool as it could be. This is the projection of B onto T. B dot T dot product scalar product divided by magnitude, that's also a scalar. This is still a scalar. And oftentimes we're really interested in vectors. So how do we do that? Well, if we want to make it a vector, make projection a vector, dot, 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 then the projection of onto the tracks of Bill, but I want to make this whole thing a vector. Well, that equals the same deal. Let's go back and look at what that was. That was b dot t over t, right? Because we have to, it's the dot product of the two, and we got to normalize it for the length of the tracks. So it's b dot t over the magnitude of the tracks. But remember, this is just a magnitude. This is the magnitude of Bill's force along the tracks. We have to add a direction. What's the direction we want? Well, the direction is in the direction of the tracks, but it has to be a unit vector. So how do we convert the track vector into a unit track vector? That becomes the track vector divided by its own magnitude. So what does that give us? Let's kind of break this down a little bit. This is the magnitude of Bill along the track, and this is green for very important, arrow winding around for very important. This is the direction of track. Now we can rewrite this one more time. We notice that there's b dot t times t over the magnitude squared. This is a scalar, the magnitude scalar. The only vector really happens here. So we can rewrite this whole thing as the projection onto the tracks of Bill vector equals b dot t, right? That's a scalar, over the magnitude of t squared times this whole thing times, and remember this is a scalar, right? So when we say multiply by, it just scales the vector t. That gets a red box. So let's put a red box around there. Now it may look weird. It's like, what? We're multiplying by the length of the entire tracks? Right? Yeah, we are. We're scaling the length of the entire tracks. But we're dividing by the magnitude of the track squared. Right? So the length of the track doesn't matter anymore. All we're going to get out of it is b times the cosine of the angle between them. And that's what you've really been doing in physics this whole time. You just didn't know the vector math behind it. All right. So there's a red box, but let's not stop there. There's a couple more cool things to do. One of which is what we call direction angles, which is kind of a funny sounding word. We can also call it, it gets even worse, direction cosines. All right, what's that all about? Let's draw a coordinate system here. That guy there. And just to mix things up, let's call that x. So what does this have? If that's x, what does this have to be? Could that be y? I don't know. We could make that y. And we could make this z. And then I'm going to draw in a vector. And this is going to get very multicolored, so bear with me. We'll draw our vector up like that. And to show you that this is kind of in 3D, what I'm going to do is drop a perpendicular down like this. But whoop, I'm dropping right down into the xy plane. And then I'm going to draw a line, another line in the xy plane that comes out to here. And then to show that this is perpendicular, draw that little guy, right? So we can see this vector is kind of coming out at us from the YZ plane. What are we going to call a vector? Let's call it, we already used Bill. We'll call it, I don't know, how about D? D vector, there. The direction angles are defined as the angle between a given vector and the particular axis we're interested in. For instance, the angle between the x-axis and the D vector, we could draw that in here like this. So these two could make two lines make a plane, right? So I could draw that in like that, and you know the closest angle, right? I'm not trying to go all the way around or anything. I'm just trying to take the angle in this plane, and that one is going to be called between x and the vector. That's alpha. Between y and the particular vector, as you might guess, is going to be called beta. And then finally between z and our vector, or alpha, beta, gamma. Right? So that goes like that. Well, I wanted the angle between this vector d and, say, the x-axis. So say I'm working on alpha. Well, that with the cosine of that alpha, at least, so let's just say the cosine of alpha, because that's easier to get. The cosine of alpha equals, well, wait a minute, that's the cosine between the angle, the cosine of the angle between a vector and an axis. An axis isn't a vector, an axis is just an axis. Oh, fortunately, we do have a vector, right? What vector goes right along the x-axis? The I unit vector. So, the cosine of alpha, if I recall, it is the dot product of d dotted with I hat divided by the product of their magnitudes. Yet again, d and the magnitude of I hat, like that. But since I know a couple things here. First of all, d dot I. Well, so that's the x component of d, the x component of I, the y component of d, the y component of I, the y component of I, whatever, the z component of d, and the z component of I. I doesn't have a y or a z component. All it has is a x component. The x component is only 1 unit long. Right, let's review, quick review. I hat equals, what is that again, 1, 0, 0. So the d component of, or the x component of d times 1 is just dx. And the magnitude of I is just 1, so it's d, the magnitude of d. Now, does that make sense? Yeah, it kind of does, because if I know that if I did it the other way, and I said, let's just do a check here, that d, the component of, in the x direction of d would be dx equals the magnitude of d times the cosine of the angle between them, which is alpha, and so that would lead us to believe that cosine of alpha equals, divide by that, so it's dx divided by the magnitude of d. Yeah, all right, so that works both ways. The cosine of alpha is dx divided by the magnitude of d, cosine of alpha is dx divided, all right, so that checks out. It makes sense. So depending on what you have, right, if you don't know the angle but you know the components, you can either easily figure out the angle, Likewise, if you need the component and you know the angle, then you can do it this way, right? It works several different ways forward and back. So to be complete, the cosine of, let's see, alpha beta would be the y component of d divided by the magnitude of d, and the cosine of gamma will equal the z component of d divided by the magnitude of d. All right, so those are direction angles. The last thing that becomes interesting at times is this concept of orthogonality. All right, what's orthogonality all about? Well, I know that the cosine of the angle is the dot product divided by the magnitudes. I mean, you've seen this enough times, but somebody will say, are you going to put that on the test? Cosine of the angle is the dot product divided by the product of the magnitudes. What if theta equals 90? What if theta equals 90 degrees? Well, that would imply, this is a big question mark there, that u, let's see, dot v, if the theta is 90 degrees, the cosine is 0. So that means the only way to make this thing 0 is if u dot v is 0. So, yeah, so, oops, that's supposed to be a, so the dot product must also be 0. So u dot v equals 0, that implies that u is perpendicular to v. Perpendicular, I'm supposed to be talking about orthogonality. Well, perpendicular kind of implies that these two are in the same plane. So I'll put that in red. Orange, how about orange for warning? Implies same plane, right? But vectors don't have a location. Let's write that. Vectors don't have location. So we can't really say u is perpendicular to v because they're not necessarily right next to each other. That's just a magnitude and a direction. So what we do say instead is that if u dot v equals 0, that implies u is orthogonal to v. All right, and that's pretty cool. So that will get a what a thin red line. Doesn't quite warrant the big thick red line. All right, orthogonality. The dot product is 0. Two vectors are orthogonal. So let's quickly review. We have, wow, we've got a lot is what we've got. Okay, we're talking about the dot product. We know that the dot product is simply the product of each individual component of these two vectors, u1, v1, u2, v2, v3, v3. We also know that if we dot two vectors together, or dot a vector with itself, u dot u, it becomes the magnitude squared. We can find the length of this vector either using the dot product or the law of cosines, and that leads us to believe that the dot product is related to the cosine of the angle between them, right? This gets a red box. We learned about projecting one vector onto another, the projection of b onto t. We can either do that as a scalar, or we can do that as a vector. We learned about the direction angles, or as it's often more convenient, the direction cosines. It's the x component, the angle with the x-axis is the x component divided by its magnitude. Same thing applies to the y's and the z's. And finally, that if the dot product is 0, the two vectors are orthogonal. That is it for the weekend. At least for me, that's it for the weekend. I hope you guys enjoy the video and come to class with lots of questions.